Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Antoine Lavoisier's 1789 Elements of Chemistry represents a deliberate architectural act, a comprehensive blueprint for a new scientific discipline constructed upon the foundations of empirical rigor and quantitative precision. This text, conceived as a pedagogical treatise, functions as a totalizing argument, systematically dismantling prior chemical philosophies through the sheer weight of its integrated evidence and the compelling logic of its new language. An examination of its internal claims, chapter by chapter, reveals a work that is simultaneously a record of discovery, a textbook for instruction, and a manifesto for a revolutionary way of thinking about the material world. This essay will undertake a direct evaluation of the claims, methodologies, and conceptual frameworks presented within the three principal divisions of Lavoisier's masterwork, assessing the logical coherence and the evidential support for the system he so carefully constructed. The analysis will proceed sequentially, mirroring the book's own structure to reveal how each part builds upon the last, creating an edifice of formidable intellectual strength and persuasive power. Section 1. The theoretical foundation and the redefinition of combustion. Lavoisier's initial section lays the groundwork for his entire chemical system, focusing on the nature of gases, the process of combustion, and the composition of acids. He commences with a profoundly influential preface that articulates his intellectual debt to the philosopher Etienne Bonnot de Condillac, asserting that a science is inseparable from the language that expresses it. This claim, that a well-formed nomenclature is itself a method of analysis, provides the philosophical key to the entire treatise. He posits that clarity of language will produce clarity of thought, a principle that informs the revolutionary restructuring of chemical terminology to follow in the book's second. The first chapter introduces a fundamentally new, operational definition of a chemical element. Lavoisier defines an element, or simple substance, as the last point which chemical analysis is capable of reaching. Any substance that chemists have failed to decompose is, for all practical purposes, an element. This pragmatic definition represented a monumental step forward, clearing away centuries of metaphysical speculation about ultimate, indivisible atoms or Aristotelian principles. The claim's strength lies in its provisional and empirical nature. He explicitly acknowledges that future analytical techniques might decompose substances then considered simple. He then presents his famous table of simple substances, a list containing 33 items. An evaluation of this table reveals the new world view in microcosm. It includes recognizable elements like oxygen, hydrogen, nitrogen, which he called acid, sulfur and phosphorus, alongside various metals. It also, quite tell Bengali bo Bengali ko mically, includes light and caloric, the fluid of heat. The inclusion of these imponderable fluids as material elements is a central, and ultimately flawed, claim of his system. He treats caloric as a substance that combines with other elements to cause changes in state. A solid combined with a certain quantity of caloric becomes a liquid combined with a further portion of caloric becomes an aeriform fluid, or gas. This conceptualization, while incorrect by modern understanding, was a powerful explanatory tool. It allowed him to unify the three states of matter within his quantitative framework and provide a physical mechanism for thermal phenomena like latent heat during phase changes. The core of this first section is his systematic demolition of the phlogiston theory and its replacement with his oxygen theory of combustion, calcination, and respiration. Lavoisier's argument proceeds through a meticulous narration of his own experiments, presented with the full force of quantitative data. His central claim is that combustion is the rapid combination of a combustible body with oxygen. He details the famous experiment involving the heating of mercury for 12 days in a closed volume of air over a charcoal furnace. He presents the evidence directly a portion of the air was consumed, and a red powder, calx of mercury, formed on a metal surface. He quantifies the change, noting the precise volume of air that disappeared. The second stage of the experiment provides the irrefutable conclusion. He collected the red calx and heated it intensely in a smaller retort, producing two substances the original quantity of metallic mercury and a volume of gas precisely equal to the volume of air that had been consumed in the first part of the experiment. This gas, which he had named oxygen, vigorously supported combustion and respiration. The evaluation of this argument reveals its sheer rhetorical and logical power. Lavoisier employs the balance sheet as his ultimate arbiter of truth. The principle of the conservation of mass, while assumed, is demonstrated with overwhelming force. What the air lost in the formation of the calx gave back upon its decomposition. The mystery of combustion was solved with an accountant's precision. He extends this reasoning to explain the calcination of metals in general, claiming that metallic calces, the substances previously thought to be the elemental bases of metals, are in fact compounds of the metal and oxygen. A metal weighs less than its calx because the calx contains the added weight of the oxygen from the air. This formulation directly inverted the phlogistonist view, which held that metals were compounds of a calx and the fiery principle phlogiston, which was lost upon combustion, somehow resulting in a weight gain. Lavoisier's argument, grounded in the unassailable evidence of the balance, made the phlogistonist explanation appear convoluted and physically impossible. He further applies this oxygen-centered model to explain the respiration of animals, which he frames as a slow form of combustion, where organisms consume oxygen and release caloric and fixed air, later identified as carbon dioxide. This claim, supported by his collaborative experiments with Pierre-Simon Laplace using their ice calorimeter, unified physiological processes with fundamental chemical reactions under a single explanatory principle. A critical evaluation of this section also uncovers a key overgeneralization that would later require revision. Lavoisier, impressed by the fact that the combustion of carbon, sulfur, and phosphorus produced acidic solutions, proposed that oxygen was the universal principle of acidity. Indeed, the very name he coined, oxygen, derived from Greek roots meaning acid former. He claims in this section that all acids contain oxygen as their acidifying principle. While this was a brilliant and unifying hypothesis for the substances he had studied, it established a dogma that would temporarily hinder the understanding of acids like muriatic acid, now known as hydrochloric acid, which contains no oxygen. This reveals how the power of his own systematic thinking could occasionally lead him to extend a Valley principle beyond its empirical support, a subtle irony in a work so devoted to empirical evidence. Section 2. The architecture of a new chemical language. The second part of the elements of chemistry transitions from establishing fundamental theory to applying it systematically. Here, Lavoisier, in collaboration with de Morveau, Berthollet, and Fourcroy, puts his philosophical claim about the identity of language and analysis into practice. The central argument of this section is that the new chemical nomenclature they devised is not merely a set of convenient labels but a reflection of the true composition of substances. The system is designed to be generative and analytical, allowing a chemist to deduce the composition of a compound from its name, and to name a new compound based on its experimentally determined constituents. The section begins by outlining the principles of the new nomenclature. Simple substances, the elements from the table in Part 1, retain simple names, some ancient like iron or copper and some newly coined to reflect a key property like oxygen, the acid former, or hydrogen, the water former. The true innovation lies in the naming of compounds. Lavoisier details the systematic rules for binary compounds, which receive the suffix "ide." The combination of a metal with oxygen forms an oxide with sulfur, a sulfide with carbon, a carbide. This was a radical departure from the old, chaotic system of names based on a substance's appearance, discoverer, or alchemical properties, such as oil, vitriol, or butter of antimony. The elegance of the system is most apparent in its treatment of acids and salts, which directly embodies his oxygen theory of acidity. Lavoisier explains that acids are formed from the combination of oxygen with a non-metallic, acidifiable base, such as sulfur or carbon. The name of the acid reflects its degree of oxygenation. An acid with a higher proportion of oxygen ends in the suffix -ig, as in sulfuric acid. An acid with a lower proportion of oxygen ends in -ous, as in sulfurous acid. This was a claim of profound organisational power, suggesting a predictable series of compounds for each acidifiable. The system's logic extends seamlessly to the salts, which Lavoisier defines as the product of a reaction between an acid and a salifiable base, typically a metallic oxide. The name of the salt is derived directly from the acid and the base that formed it. A salt formed from an ic acid receives the suffix -ate. Thus, the reaction of sulfuric acid with potash produces potassium sulfate. A salt formed from an ous acid receives the suffix -ite. Therefore, sulfurous acid reacting with potash produces potassium sulfide. An evaluation of this framework reveals its immense utility as a cognitive tool. It transformed chemistry from a mnemonic exercise of memorizing arbitrary names into a logical discipline. The nomenclature created a map of chemical relationships, allowing practitioners to predict the existence of certain salts and to understand instantly the family of compounds to which a substance belonged. The very structure of the language guided chemical thought and experiment. A critique of the claims in this section must again focus on the limitations imposed by Lavoisier's own theoretical commitments. The entire nomenclature for acids and salts is built upon his claim that oxygen is the sole principle of acidity. The system provided no logical space for an acid lacking oxygen. When chemists later definitively showed that muriatic acid was a compound of hydrogen and chlorine, the nomenclature required a significant revision. This demonstrates that while Lavoisier's system was powerfully analytical, its direct link to a specific theory made it vulnerable. The language was so perfectly tailored to the oxygen theory that it could not easily accommodate data that contradicted that theory. It reveals the double-edged nature of his project. The tight coupling of language and theory creates immense intellectual momentum, but also generates blind spots. Nonetheless, the core principles of his systematic nomenclature, particularly the use of suffixes to denote composition, proved so effective that they remain the basis of inorganic chemical naming to this day. This section of the book, in essence, provided the software for the new chemical hardware detailed in the first and third. Section 3, the instruments and operations of a precise science. The third and final section of the elements of chemistry is a detailed description of the tools and techniques of the new quantitative chemistry. This part is Lavoisier's ultimate grounding of his theoretical claims in concrete, repeatable, physical operations. The central argument of this section is that the truths of the new chemistry are accessible to any practitioner who possesses the correct instruments and follows the correct procedures. It is a work of radical transparency, laying bare the methods behind the revolutionary conclusions of Part 1. By demystifying the laboratory, Lavoisier makes his science a public and verifiable enterprise, a stark contrast to the secretive and often obscurantist traditions of alchemy. The section functions as a detailed laboratory manual. Lavoisier provides intricate descriptions and engraved illustrations of the advanced instrumentation required for his research, much of which he designed or commissioned himself. A key instrument presented is the precision chemical balance. His evaluation of its role goes beyond mere measurement. Lavoisier presents the balance as the primary instrument of chemical logic. His entire system, from the refutation of phlogiston to the analysis of water, rests upon the equation or balance sheet, where the total mass of the reactant must equal the total mass of the products. The precision balance, capable of measuring to fractions of a grain, was the technology that made this principle an empirical certainty rather than a philosophical assumption. The claim is that chemical transformations are governed by a strict economy of matter, and the balance is the tool that audits this economy. He provides an equally detailed account of his apparatus for handling gases, including the pneumatic trough and the gasometer, a sophisticated device for precisely measuring, storing, and transferring gases in experiments. Before Lavoisier, gases were understood as vague airs, difficult to manage or quantify. The gasometer transformed them into distinct chemical substances with measurable volumes and, when combined with the balance, determinable densities. By detailing its construction and use, Lavoisier is making a powerful claim: the ephemeral world of aeriform fluids has been brought under the dominion of quantitative science. The ability to manipulate and measure gases with this level of precision was essential for his experiments on combustion, respiration, composition. A further focus is the ice calorimeter, which he developed with Laplace. Lavoisier ascribes its design and operation for measuring the heat evolved during chemical reactions or physiological processes. The principle is to measure the quantity of heat by the mass of ice it melts. This instrument embodies his claim that even caloric, his imponderable fluid of heat, could be subjected to quantitative analysis. The calorimeter represents a heroic attempt to bring thermal phenomena into the same balance-sheet framework as mass. The claim is that heat is a measurable quantity that is conserved or transferred in predictable ways during chemical change, just like matter. This completes the unification of his system, demonstrating that his chemistry could account for both the material and the energetic transformations in a reaction. By including these detailed instructions, Lavoisier was not just reporting his results, he was disseminating a new culture of scientific practice, one founded on precision instrumentation, meticulous procedure, and the primacy of quantitative measurement. The strength of this section is its incontrovertible link between theory and practice, proving that the abstract principles of his chemistry were the direct result of tangible laboratory operations. Conclusion: Antoine Lavoisier's Elements of Chemistry achieves its revolutionary impact through the perfect synthesis of its constituent parts. An internal evaluation of its claims reveals a work of exceptional logical and rhetorical coherence. The first section advances a new theory of matter and transformation, grounded in the operational definition of an element and the quantitative oxygen theory of combustion, all verified by the evidence of the balance. The second section constructs a new language for the science, a nomenclature that is itself an analytical tool, directly reflecting the compositional principles established in the first part. The third section provides the methodological foundation, detailing the instruments and procedures that make the entire system empirically verifiable and reproducible. Each section validates and reinforces the others, creating a closed and powerfully persuasive intellectual system. The core claims of the treatise of conservation of mass, the role of oxygen in combustion, the compositional basis of nomenclature, and the necessity of quantitative measurement collectively established the paradigm for modern chemistry, while a close analysis reveals certain flawed theoretical commitments, such as the material nature of caloric and the universal acidity of oxygen. These are less failures of the system than artifacts of its own internal logic and the available evidence of the time. They are the scaffolding that Lavoisier used to erect his permanent structure. The work's ultimate genius lies in its unification of theory, language, and practice into a single, indivisible whole. It did more than report discoveries, it provided the definitive blueprint for a new science, transforming chemistry from a qualitative craft into a rigorous, quantitative discipline. The Elements of Chemistry stands as a testament to the idea that a scientific revolution is a comprehensive act of reconstruction, requiring not only new facts but also a new way of speaking, seeing, and measuring the world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.